In this slidecast, we'll discuss heap sort. Now, merge sort time is order n log n, but it requires temporary storage locations and extra ones. Heap sort is interesting because it doesn't require any additional storage. Now, as its name implies, heap sort uses a heap to store the array. So this is the heap data structure that we discussed in the prior chapter. Now remember, a max heap is a data structure that maintains the largest value at the top. So once we have a heap, we can remove one item at a time from the heap. And the item removed is always the top element, and we'll place it at the bottom of the heap. And then when we reheap, the larger of a node's two children is moved up the heap, so the new heap will have the next largest item as its root. So if we continue to remove items, the heap's going to shrink as the number of items are removed. And if we implement the heap using an array, then each element removed will be placed at the end of the array, but in front of the elements that were removed earlier. So after we remove the last element, the array will be sorted. So here's a picture. If we draw our heap as a binary tree, remember the property of the heap is that the largest value is at the end. So we'll start out, since 89 is the largest, we'll switch that with the last element, so that now 89 is in the last position in the underlying array, and now we'll reheap by moving 6 to its proper location. So we'll move up 76 is the largest item, then 37 is the largest child, and finally 26 is the largest child. So now the remaining structure is a heap with the largest value of 76 at the root of the heap. So we'll take 76 and switch that with 29, and we'll continue. We'll bring up 74 and then 66. So now the final two items are sorted, and the remaining structure is a heap. We'll take 74, swap it with 28. 28 we'll swap with 66, and then with 39, and then we're finished. It's in its proper place. We'll take 66, switch with 18. Now we need to recreate our heap by moving 18 down to the leaf. So now 39 is the largest value in the heap. We'll swap it with 6. We'll take 6. Again, at every step we switch it with its largest child. Now the largest item is at the root of the heap again. So we'll take 37 and exchange that with 20. And 20 will exchange with 32 and with 26. And we just continue the same procedure. 32 gets swapped with 18. We'll go ahead and readjust our heap. Then we'll take 29, swap it with 18. Again, we'll go ahead and adjust our heap. And we just continue this process. 28 gets switched with 6. 6 will switch with 26 and then 20. 26 will insert where 6 is. And we're just continuing this process until finally we take 20, swap it with 18. Got two items left in the heap. We'll go ahead and exchange, or we'll leave them alone. Now 18's the largest value. We'll place that here, and 6 is at the root, and now 6 is in its sorted location. So we always take the root element of the heap, place it where it belongs in the sorted array, and then adjust our heap structure. Now remember, if we implement the heap as an array, then each element removed will be placed at the end of the array, and then the heap part of the array decreases by one element. So if we started with 89 as the largest, and we swap it with 6, 89 goes here. Once we readjust our heap, 6 gets moved to this location, and then we take 76 and place it near the end. And then the light blue is our heap. And so we just continue doing that until eventually everything is in sorted order. Here's the algorithm for doing this in-place heap sort. So we build a heap by rearranging the elements, and while the heap's not empty, we remove the first item and swap it with the last item in the heap, and then we restore the heap property. Now if we want to sort the sequence table bounded by the iterators first and last, we can consider the first item to be a heap of one item. And we now consider the general case where the items in the sequence from table sub first through table sub first plus n minus 1 form a heap, and the items from table sub first plus n through table sub last minus 1 are not in the heap. And as each item is inserted, we must reheap to restore the heap property. So here's a refinement of step 1. We say that while n is less than the table length, we increment n by 1, and this inserts a new item into the heap. Then we can restore the heap property. Now, because a heap of size n is a complete binary tree, it has n levels, and building the heap requires finding the correct location for an item in the heap with log n levels. So each insert or remove is order log n. And with n items, building a heap is order n log n, and there's no extra storage space needed. Here's the code from the author. We've got a heap sort routine that starts with a build heap and then calls shrink heap. And here's our build heap function. It uses iterators, and it uses those calculations we talked about in the last chapter about how you find the parent and child in a heap. And then here is shrink heap, transforms a heap into a sorted sequence. So come and look at this code on your own and make sure you understand all the steps of what's happening. And that brings us to the end of this slidecast.